Okay, I'll just, okay, this is just a basic example of calculating the factorials using recursion. You want to have a recursive equation. The n factorial is equal to n times n minus 1 factorial. And if you don't have a base case, it's going to run forever because it's going to keep on calling itself. So in this case, our base case is what we're going to return without calling the function again. So we're just going to return 1. Now, in this example generates all combinations of strings of length 3 that contain the digits 0, 1, and 2. So you can see here, this is the output. And if we scroll through, there's 27 different combinations of 3-digit strings that contain these numbers. And what we're going to analyze how this recursion works because it uses this technique called backtracking. And we're going to discuss that before we go into the end queens problem because it's important to understand. And this state space tree that we're going to look at is just a diagram for understanding how the recursive calls take place and what order they take place in. So this code is it's pretty basic. We have this recurse function and it gets called with an empty string. Inside of our actual recurse function, the way that it works is if the string is of length 3, it just prints it out like we have over here 0, 0, 0, 0, 1, and so on. If the length is not yet 3, we still have to add more digits to it. So we'll call whatever the string is currently, maybe like it starts off as an empty string. You can see over here, it starts out empty. So it's going to add a 0 to it and call recurse with that 0. It's going to add a 1 to it and call recurse with that 1. And it's going to it's going to add 2 and then call recurse with 2. And it's going to keep on doing this until the length is 3, at which point it prints it out and it's done with that combination. So if we draw if we draw a diagram showing how these recursive calls take place, we start off with an empty string in the first step. And then the first line that it comes to is line 8 over here. And it's important to understand in recursion, it's going to go all the way down until until it finishes all combinations for a particular recursive call. So it's going to add 0 to this empty string. And even though later on it's going to try combinations where the first digit is a 1 and the first digit is a 2, it's going to explore every single combination where the first digit is a 0. So let's take a look at what that's going to be like. So we have our empty string and then it calls recurse with 0. This is what s is equal to at each step. And so now s is equal to 0 and the length is not 3. So it's not going to print it out yet. And now it has these 3 lines of code to look at. It's going to call recurse of s plus 0. So now it's going to call recurse with 0, 0. 0, 0 does not have a length of 3. It has a length of 2. So once again, it's going to have to call these 3 again. It's going to come to this else statement. And then it's going to call 0, 0, 0 over here, the s plus 0. And that's going to be 3 zeros, which has a length of 3. So it prints it out. And that's the first thing we see in the output. So now it's done calling recurse. It's done calling recurse 0, 0, 0. It's done calling this part over here. It just finished it and it printed it out. So now it's going to come back up the tree to 0, 0. And the next thing, what's the next thing it's going to do after calling recurse of 0, 0 plus 0? What's the next line of code? It's this one over here. It's recurse of s plus a 1. So s is equal to 0, 0. We're back here. It's going to call recurse of 0, 0, and then 1. And then it's going to print that out because the length is 3. And then there's nothing else. That recursive call is done. This recursive call over here is done. So now it's going to go and call recurse of s plus 0 plus s plus 2, this line over here. So we get 0, 0, 2. And now it's done all combinations where s is equal to 0, 0. It's finished all 3 lines when s equals 0, 0, and we printed out the result. So it's going to go all the way back to where 0, 0 was called in the first place. 0, 0 was called back when s was just 1, 0. Back when s was just 1, 0 in line 8, we called recurse of s plus 0. And s was 0. This is a 0. This is where 0, 0 was called. And we just finished doing the stuff at 0, 0. We printed all combinations. So now we're going to go to line 9. And the next thing is going to be 0, 1. And then again, just like as we did before with 0, 1, with 0, 1, the first thing that's going to be called is 0, 1 plus 0. So that's going to give us 0, 1, 0. And then it's going to call 0, 1 with a 1. and then 0, 1 with a 2. And now it's done with all combinations of 0, 1. So it's going to go back to where S was just a single 0, and it's finished this part over here. It's finished this part over here with 0, 1. The next thing to do is 0, 2. So now you guys kind of get an idea of how it works. So just to clean this up a bit, just to clean this up a bit, the way that it's going to work is it starts with this empty string, and it adds 0 to it, then it adds 0 again, and then it adds 3 zeros, and then it adds 1, and then it adds 2, and then over here it adds a 1 to it, and then a 0, and then a 1, and then a 2. And this is the tree that we get through these recursive calls. And it's backtracking because once it tries a combination, once it tries adding a 0, it's going to come back and it's going to go to the next line and try adding a 1. And this is important to understand for the n-creams problem. So are there any general questions about the factorial stuff or how recursion works? When you make a recursive call, it's going to go and finish that recursive call completely before going on to the next lines. Okay, so now we're going to go ahead and do the n-creams problem. Just a second. I'll explain the n-creams problem while I'm doing something. So the n-creams problem is basically a problem in which you have an n times n square board made up of little 1 by 1 squares. And you have to place n queens on the board so that the queens can't attack each other. If you've ever played chess, then if queens are in the same row or if they're in the same column, they can attack each other. And if they're also diagonal relative to each other, they can attack each other. So you want to print, the goal for this problem is to find all the different ways to place the queens on the board so that no two queens can attack each other. And this is an example where you want to code hands-on because there's no point in just watching me type it. You want to be doing it as well and practicing because there's a lot of skills you can learn from this. And the stuff that we've been covering recently, like greedy algorithms, recursion, these are advanced concepts that come up a lot in contests, in more advanced contests. A little bit in the competitions we compete in at school, but in like harder contests and college contests and stuff and job interviews. So you want to make sure you're following along hands-on so you can ask questions. Okay, but let's go ahead and get started with this problem. We're going to, just like we have in the previous problems, we're going to write a recursive function. Now, why can't we write a for loop? If we knew for a fact that the board was always going to have a size of 4 times 4, we could write like 4 for loops. We could write a fixed amount of for loops to do the problem for us. But because the board can be any size, writing a fixed number of for loops is not going to work. We're going to have to use recursion. So I'm just going to start with some basic stuff. I'm going to have a character board. This is going to be representing our game board. And I'm also going to have an int.
Your screen's not shared.
Oh, okay, thanks. Thank you for telling me early instead of like 5 minutes later. Okay, so now you guys can see my screen. And so I just have huh?
We were just saying that we can see it.
Good. So we have a character board. This is going to represent our game board, our chess board. And then we have n, which is the size of the board. So board is going to be a new character board of size n by n. And then we already have the value of n set. And now what we're going to do is we're just going to have a for loop. And we're going to go through each row in board. And we're going to say arrays.fill row with periods. All this does is just fill our character board with periods. And whenever there's a queen, we're going to use the character Q. If there's nothing in that spot, we're just going to use a period. So that's what I did over here on line 12. I just filled it with periods. Now we're going to write a recurse function. And this is how a recurse function is going to work. We're going to go row by row and add queens to every single combination, every single place that we can. So we have like our game board over here. In this example, we're going to keep it simple. Towards the end, we'll make n larger and see how fast it runs. We have our game board. And what we're going to do is go row by row and try every single place that we can place a queen. We're going to place a queen here, and then we're going to try placing queens in the remaining 3 rows. We're going to try placing a queen over here, and then try placing in the remaining rows. Place a queen here. We're going to try every single spot in each row. So let's take a look at how we'd code this. Our function is going to be public static void, and we're going to, its parameter is the row number. And just like with the factorials, just like with this public class example, we want to have a base case. And that base case is if the row is equal to 4, then we have to print out board later. We'll code that later. But anyway, if the row equals n, we'll use n instead. Because we're going row by row, we start off when row is 0, and then we go to 1, we go to 2, we go to 3. As soon as row becomes 4, that means we're done filling up our board because 4 is out of bounds. And n is equal to 4. That's what we said over here. So now for the actual logic of trying every single combination for each queen. Because we're doing this recursively, all we have to worry about is placing a queen in each column of this current row. So we're going to have a for loop and we're going to have a column variable. And what we have to do once again is we have row is equal to 0. We're going to try to place a queen at every single, in each column, one at a time. We're going to try placing a queen here, then here, then here, and then here. So we're going to have a for loop where call, which is our column number, starts at 0. And it's going to go up to n, and it's going to increase, just a regular for loop for a column variable. And then what we're going to do is we want to try putting a queen at this position. So we're going to say board of row of call equals q. And then we're going to make our recursive call with row plus 1, because we just finished putting a queen in this row. So we're going to go on to the next row. And we're going to put a queen there, and then the next row, and the next row, and so on. And after this recursive call, this is the part where backtracking comes in. So just imagine a state space tree. We start at row 0, we place a queen at column 0. After we try every single combination where the queen is in this top square over here, we now want to try every combination where the queen is here. So that's why we have to reset this position back to an empty square. We're going to put a period over here. So just to reiterate, we have our for loop. We're going to try this position being the position where the queen is. So that's why we set it a q. We make our recursive call. Remember, the recursive call is going to go all the way deep. It's going to try every single combination. And after that recursive call is done, after line 14 is done, we're going to reset this to an empty space. Okay. And over here, what we can do is print out our board now. So if row is equal to n, we're going to print out our board. And we're just going to have another for loop like we did before. 4 rows in board array. We're going to print out arrays.toString rows. And we're going to add a little dash line to separate our output. And then we're going to return. This return over here basically means return out of the function, don't run any of the code below it. So it's not going to run this for loop. Let's just take a look at what this looks like. And if I'm going too fast or you want me to explain anything, please, you can let me know. Okay, so you can see here, it's printed out every single combination of our board that we could have with 1 queen per row. So I'm going to scroll all the way to the top. You can see the queens started all in the same column. And then the bottommost queen went to column 1, then column 2, then column 3. And then it finished all combinations where the first 3 queens were in the same row. So then it backtracked. And then for row 2 over here, it moved the queen to column 1. And then it started moving the bottommost queen again. So once again, if you were to draw the state space tree for this, you would understand why. Because the order our recursive calls are going in is it starts at column 0, and then it goes to 1, 2, 3, 4. And once it finishes all the combinations, it's going to go back up to the higher row. In this case, it's going to go back up to row 2, and then it's going to move the queen at row 2. And it's going to keep on moving the queen at row 2 to the right until it finishes. And then it's going to go back to the queen at row 1 and move the queen at row 1. So are there any questions about this so far? Okay, so this is not what we wanted, obviously, because it's violating some of the rules. We can see that there are queens who are in the same column as each other. And the whole point of this problem is to print out every combination where the queens cannot attack each other. So what we are going to do is going to have a Boolean array. So we'll have a static Boolean array called call used. and it's call used. And what this Boolean array tells us is whether a column has been used. Because let's say this queen over here takes up column 0. If column 0 is used by a queen, we don't want to use it for any of the later queens. So that's the logic behind this. We're going to keep track of which columns are used. And then if a column's used, then we're not going to use it. If it's not used, we're going to try that combination. So we're going to go into our main function and we're going to say call used equals new Boolean n. And now inside of our for loop, we're going to add some logic. We're going to check if this column has been used. So if call used call, well, we want to check if it's not been used. So if it's equal to false, that means this column hasn't been used yet. So I'm just going to cut this code and I'm going to put it in here. So if this column has not been used, we're going to make this a queue. And then this is important. We also want to, now we want to mark this column as used because we're testing it out with a queen. And just like we did with the board, we backtracked and we reset it. We're going to reset call used of call to false. So we have our two statements before the recursive call. We put a queen over here and we mark the column as used. Then we make our recursive call. After the recursive call is completely done, we're going to come back, reset this to an empty period, and then see that this column is not being used. Okay, let's just try running the code with this and see what difference we get. So I'm just running this. And you can see immediately we don't have like a million different combinations output. We only have a few of them. We have like 24 or something, I think. And you can see in all these combinations, the queens are not in the same column. So did everybody understand this, how this worked? Are there any questions? And if you also need me to copy and paste my code into the chat, you can let me know. I just want to make sure everybody's following along. So if you guys could just type something into the chat or unmute yourselves, that would be helpful. Is everybody here?
Someone in chat wants you to post the code.
Oh, okay, thanks. I didn't see that.
Yeah.
So can anybody remember, based on what I said the problem statement was for this problem, whether we've solved it or not? There's one last thing we have to do, and what's that? I'll give you a clue. Look at this.
And we need to look at the diagonals because queens also attack diagonally. So
yeah, we have to look at whether the queens are there are queens in the same diagonal. So this over here checks whether or not the queens are in the same column. We're going to write a function called diagonal find. And what this function will do is it will return true if the current arrangement of queens are not like hitting each other in the diagonals. That's fine. Otherwise, it will return false if it's not fine. And we'll take in the row number and column number. Another thing that we have to know is which column a queen in a specific row is at. So we're going to create another array over here called static int which call. And this column, which call of row, tells us which column the queen at row is located in. So that's what it tells us. We provide it with a row number and it will tell us which column that queen is located in. And inside of our main function, we'll have which call equals new int n, because there's only n rows. And one more thing we'll have to do is whenever we choose to put a queen at a specific position, we're going to have to say which call of row equals call, because we just placed a queen. The queen at position row, the queen in row number row is at column number call. That's what we're doing over here. And now we're ready to write our diagonal find function. But does everybody understand the logic behind this? We're going to keep track. Given a row number, we're going to keep track of which column the queen is located in. And then we're going to eventually use this in our diagonal find function. Okay, this is what the code looks like now. We're going to go ahead and write our diagonal find function. This is a Boolean function that returns whether or not the queens are fine based on their locations to each other, respective to whether they can attack each other diagonally. And it'll take in a row number and a column number. So now what we want to do is because we know the row number we're at, let's just say for this example, we're in row number 2. So we have queens over here. we want to check for a given row number whether any of the previous queens before it are in the same diagonal as it. So we're going to say for int previous row equals 0, previous row is less than row, previous row plus plus. We want to check whether or not that this queen on the previous row collides with this queen on this current row. And one thing you'll notice is if two queens can attack each other diagonally, that means the difference between their row numbers and their column numbers is equal. So just take a moment to understand that. If I have two queens who can attack each other diagonally, the distance between their rows, which is 2, is equal to the distance between their columns, which is 2. So what we can do over here is we can create a variable for the previous column number, previous call. So we want the column number where this queen is located. And because we have this which call array over here, we can just say which call of previous row. And what we're going to do is we're going to check if the difference between the rows of these two queens, so just as I showed earlier in that little diagram, if the distance between the rows is equal to the distance between the columns minus call, then that means these two queens can attack each other diagonally. So we're going to return false. This diagonal is not fine because they can attack each other. Otherwise, outside of our for loop, we're going to return true. And now if we run this, this should be the complete solution to the n queens problem. So let's go ahead and run it. And you can see it only output 2 diagrams for us, 2 boards. And if you look at them, we have the queens, each in their own row, each in their own column, and they're not attacking each other diagonally. Same thing over here. And it turns out for a board of size 4, for a 4 times 4 board, the answer is going to be 2. Let's try 6. Let's try 6. So I'll come over here to line 7, change n to 6 and run it. And our code will work for any size of n. And you can see over here for 6, it printed out 4 different boards. You can see them over here. It printed out 4 boards. And you can go ahead and try large numbers like 10. And you can see we got a large board printed out, and there's multiple of them. There are multiple answers for 10, obviously, because it's a large board. And you can check any one of them and it'll be correct. But this is the solution to n queens. Are there any questions about how it works? Any questions at all about the code? This is important to understand. Next week, if you remember, like a couple of months ago, we covered a BFS, the BFS algorithm, breadth first search, and I had a PowerPoint on it and everything, and we did some coding examples. We're going to be covering a DFS next week. So you have BFS, which is a breadth first search. It starts at one point and it goes step by step to the points closest to it. And then you have a depth first search, a DFS, which goes all the way out in one direction, then all the way out in another direction, and all the way out instead of like going by distance. So that's what we're going to be covering next week. So you're going to make sure you understand recursion. If there aren't any questions, then I have a question for you. What do you think is the time complexity of this program? You can take a guess, but before you take a guess, make an educated guess. Try to understand it. Think about the factorial one. What's the time complexity of this? And then try to think of the time complexity for n queens. Try to think about how many times this function is being called and how it's being called. Think about the state space tree.
Is the complexity the factorial one just O of n because it calls the factorial function n times?
Yeah, the complexity of the factorial one is just n. This one over here is going to be whatever your length is. Whatever your length is to the power of how many of these digits there are. So if I added a third digit, it would be 3 to the 4th. And then, sorry, the other way around, 4 cubed. It would be 4 cubed, 4 to the 3rd. And then over here, are there any ideas? O of n squared. Okay. So, n squared is a possibility. But you should note that each recursive call is located inside of a for loop. Yeah, so the time complexity of this is actually n factorial, because it's going to start off calling row when row equals 0, And then when rows equal to 0, it's going to try columns 0, 1, 2, and 3. For each of these columns, maybe it'd be better if I drew this out somewhere just a second. But yeah, it's roughly n factorial, and of course we have this over here, which is about n, so it's n factorial times n, but that doesn't matter, it's just n factorial. So let me delete this. Okay, so what's going to... Huh?
Is this the fastest way to do this problem?
I'm sure there's probably some constructive way to do it.
Oh, okay.
You can search it up. I'm not too sure. I know this is an n factorial way to do it. Maybe there's some like actual constructive algorithm where there's a smart way to build it up. But yeah. Okay, so this is, we're gonna I'm going to be drawing about 4 rows, and each row is going to represent a different row number. So first we're going to start off at row 0. And for row 0, we have an empty board right now. So we have an empty board with no queens. And then we're going to try placing the queen in row 0 at column 0. So like these numbers over here represent the columns, and the numbers, the actual row that it's on represents the row number. So we're going to try placing a queen at row 0, column 0. And then for row 1, we're going to try placing a queen at column 1, column 2, column 3. For this combination over here, we're going to try placing a queen at row 2, column 2, column 3, and then so on. You get the idea. So at each step, in the first step, there are n places where I can keep the queen. If I have this row over here, there's n columns where I can keep the queen. Let's say I put the queen over here in the second column. Now for the next row, there's only n minus 1 places I can keep it. And then after that, there's n minus 2 and so on. So that's why it's n factorial. Because remember, we're also trying every single combination, every single place to keep the queen. And as Kanishk pointed out, that's why the complexity is not that great. It's about n factorial, which means for 10 factorial, it worked fine. Let's try something like 15 and see how fast it runs. So you can see it's still running. You can see that it's still giving out output. And I'm just going to stop it now because it'll take a really long time. But yeah, so that's the n queens problem. And I'll put the full code into the chat. Are there any additional questions about it? Let me try copy. Is it too big to put in here? Yeah, I think it's too big to put in here. Maybe I'll put it on the club's GitHub or something. I'll just copy the diagonal fine and recurse functions now that they're complete. Okay, so there's no additional questions. Thank you for coming, and you guys are free to go. If you have any questions, you can stay behind.